Why do SSDs have weird sizes? Why do SSDs have sizes like 240 GB or 120 GB rather than the normal 256 GB or 512 GB? Those numbers make much more sense than 240 or 120.
While a lot of modern SSDs like the 840 EVO series do provide the sizes you're used to, like the mentioned 256 GB, manufacturers use to preserve a bit of storage for mechanisms fighting performance drops and defects. If you, for example, bought a 120 GB drive, you can be pretty sure that it's really 128 GB internally. The preserved space simply gives the controller/firmware room for stuff like trim, garbage collection and wear leveling. It has been common practice to leave a bit of space unpartitioned, on top of the space that has already been made invisible by the controller, when SSDs first hit the market, but the algorithms have gotten significantly better, so you shouldn't need to do that anymore. Edit. There have been some comments regarding the fact that this phenomenon has to be explained with the discrepancy between advertised space, stated in gigabytes, for example 128 x 10 to the power of 9 bytes, versus the gigabyte value the operating system shows, which is, most of the time, a power of 2, calculating to 119.2 GB in this example. As far as I know, this is something that comes on top of the things already explained above. While I certainly can't state which exact algorithms need most of that extra space, the calculation stays the same. The manufacturer assembles an SSD that indeed uses a power of 2 number of flash cells, or a combination of such, though the controller does not make all that space visible to the operating system. The space that's left is advertised as gigabytes, netting you 111 GB in this example.
Both mechanical and solid-state hard drives have raw capacity greater than their rated capacity. The extra capacity is held aside to replace bad sectors, so the drives don't have to be perfect off the assembly line, and so that bad sectors can be remapped later during use to the spare sectors. During initial testing at the factory, any bad sectors are mapped to the spare sectors. As the drive is used, it monitors the sectors, using error correction routines to detect bit-level errors, and when a sector starts going bad, it copies the sector to a spare, then remaps it. Whenever that sector is requested, the drive goes to the new sector, rather than the original sector. On mechanical drives, they can add arbitrary amounts of spare storage since they control the servo, head, and platter encoding, so they can have a rated storage of 1 TB with an additional 1 GB of spare space for sector remapping. However, SSDs use flash memory, which is always manufactured in powers of 2. The silicon required to decode an address is the same for an 8-bit address accessing 200 bytes as an 8-bit address accessing 256 bytes. Since that part of the silicon doesn't change in size, then the most efficient use of the silicon real estate is to use powers of 2 in the actual flash capacity. So the drive manufacturers are stuck with a total raw capacity in powers of 2, but they still need to set aside a portion of the raw capacity for sector remapping. This leads to 256 GB of raw capacity providing only 240 GB of usable capacity, for instance.
Simply put, all SSDs are, at base, not what they advertise. What they advertise is the usable disk space. For most drives with 120 usable GB of storage, the base drive actually is a 128 GB drive. 8 GB is reserved for some specific background management tasks, as stated before. Now, technically they could slap another chip on the piece to give you 128 GB of usable space, but that costs more money. The companies making drives have realized that people care more about how big their drive is than whether its usable space is actually a multiple of 2. Side note, there are actually a few ways of writing the required system code, which is why you'll see 120, 124, and 128 GB drives from different manufacturers. They all have 128 GB of raw space, but they handle the required background stuff differently. No version of the drive coding is so much better than the others that you'd notice it in most cases. You might notice a slight difference in performance benchmarks, but you're very unlikely to notice it unless your computer is doing some heavy lifting and you know what to look for.
Growing by powers of 2 is a strictly mathematical concept that makes it easy to take math shortcuts in a computer that's based on 2 states. That is to say that a computer can perform integer multiplication or division by a factor of 2 as easily as you can multiply or divide a number by 10. You simply shift the digits left or right without having to actually perform a calculation. Every programming language has an operators for these simple operations. In C-like languages, they are n and gt semicolon and gt, m, aka shift and write m bits, aka divide n by 2 to the power of n, and n and lt semicolon and lt, m, aka shift left, aka multiply n by 2 to the power of n. Inside the processor, this operation generally takes 1 cycle and happens to the data in place. Any other arithmetic operation, like multiplying by 3, requires invoking an ALU, arithmetic logic unit, to spend an extra cycle or 2 marshalling the bits around and copying the result back to a certain register. Heaven help you if you need decimal point precision in the floating point unit gets involved. Anyhow, this is why your computer likes to refer to everything internally as powers of 2. If the machine had to go to an ALU operation every time it wanted to do some simple math to calculate a memory pointer offset, your computer would be running an order of magnitude slower. The growth of physical storage, on the other hand, is governed less by raw binary math than it is by physics, engineering, and chokes on the word marketing. With the spindle disk, the capacity is determined by the number of platters, the size of the platters, the size of the cylinders, and the number of sectors that can fit into a cylinder. These are generally determined more by the physical capabilities of the hardware and the precision of the read/write heads than anything else. I'm not as intimately familiar with the internal characteristics of SSDs, but I imagine that the scaling is based on: we can build an array of n x m non-sectors, layer them k deep in a chip, and fit j chips m into a 2.5 inches HDD case. Reserve H% of them for performance optimization, round the number down to the closest multiple of May 10, 2020, and that's the capacity of the drive we're going to print on the box. Having any of those calculations work out to a neat little power of 2 will be a complete fluke and of little benefit to anyone.
If you want to support the channel, please consider subscribing.